good afternoon, everybody. This is Paul Taubman with 9.Connects. Thank you very much for joining us here today. You are in the right place if you are here for our webinar on auto routing. So just before we begin, just want to give you a little bit of a heads up. We may not have time to answer questions today. Originally, when I went through the initial sequence of all the slides I had, it went out to about 2 hours, and I'm not sure if that was because of edits and touch-ups, but obviously we can't go that long. So I did trim it up quite a bit, and so I think I can get it under an hour, but I think it'll be just under an hour. If you have any questions, feel free to write those questions in the questions panel that comes with the webinar panel. And I do ask that you be specific about it so that if we have to get back to it later, then we can answer it properly. If we can't get to it today, we'll either respond by following up with email. If we get a number of questions, we'll put together our Q&A sheet, and we may be able to give you an immediate response too. There's other people, though they're not necessarily speaking today, they are checking those questions, and they may be able to assist you in the background there. So that's what we're going to do here. Just one other quick note, though you will see slide pictures from Altium, because that's where we did most of our experimentation, this is not a webinar on how to use the Altium Situs Autorouter. We'll make references to it, and we'll explain what that router is doing, because that router is very similar to other PCB routers, but this is more of a general purpose, trying to give you a full overview of what you can expect from a router, how the router reacts, and what you can do to kind of tame the router. Okay, so I just want to give that heads up and that expectation. So first and foremost, the purpose. What is the purpose of an auto router? The auto router is to speed up the layout process, and I think that we have a expectation that in this day and age, with all of our technology, that the auto router should do amazing things. But really, we've got a little bit of an issue with that, because when it comes to it, we're trying to take our design process and turn it into an assembly line process. And there are, let's say, overtones that are similar to each other, but that's not necessarily the case. And I want to give you kind of a better example of this. You know, in the design area, really all we need to do is design one time. It's a prototype. And I give this example of this mechanical pencil over here. There was only one design that needed to be made, and now from that design they make millions of these mechanical pencils. Okay? So we have to remember that the design process is custom and it is a prototype. We just have to make one of them. So every time we get to another project, that we are following a flow, which looks a lot like an assembly flow, really each one of them is a custom operation, and routing is definitely a custom operation. The other thing too is that assembly is very, very repetitive. Okay, we do things many times, and we make many, many copies. And I wanted to give this example over here of a plastic bottle maker. So Coca-Cola, for example, has a facility that does nothing but makes bottles all day long. They make millions of bottles. That's all it does. They don't fill them, they don't label them, they don't cap them. This facility makes bottles. And this is one of the machines that they've got in order to do it. And it's a pretty amazing machine. And it can put out hundreds of bottles in very, very little periods of time. But understand that this machine, pardon me here, let's go back to that. This particular machine is dedicated for that particular function. It does nothing else but makes bottles. And if you want to make some other plastic good, then you would have to completely retool that machine to do that. And so that's what we have to remind ourselves of when we look at these things, that the assembly process is a repetitive science. It's a repetitive process. It really is a science, whereas we're in design, and the whole idea of design is an art. So there's really the difference between the two of them there. Now, believe it or not, just because we don't look at auto routers, I think in the perspective that they need to be looked in, doesn't mean that nobody's using them. As a matter of fact, there's a lot of research going on in auto routers all the time, and there's actually 3 major industries that are looking into this. So first and foremost, the internet, because yes, you have traffic flows, and a lot of times what they're trying to do in the internet with these quote-unquote auto routers is they're trying to move things through the internet so you don't have bottlenecks. For example, if someone is asking or requesting for a video, as far as the individual is concerned, they just want to see the video in real time. Now, whether or not they see the buffering or not behind the backgrounds, they don't care as long as there's no skips or interruption in the video. But that's what the network trafficking can do, or the internet routing things can do. Or if there's an email being sent out, can it be held off another 5 seconds? Certainly can, right? I mean, I know there's times we really need an email very quickly, but the fact of the matter is we can get an email, definitely under 30 seconds, and we'll get it, rapid speed. So the internet is interested in trying to find the fastest paths. and to keep the traffic moving. Another area is artificial intelligence, and interestingly enough, most of the routing things that we see today came from investigations in artificial intelligence back in the 1960s and 1970s. Okay, and what were they trying to find, or what were they trying to do with it? They're trying to figure out how do we get a device to navigate itself from point A to point B, especially if there's obstacles in the way. And we're going to see this as we kind of go along here today when I show you a couple of examples of routing types. And then lastly, in one particular industry which is really kind of close to us is the computer chips, or the ASIC industry. And they use something called place and route, which is also auto routing. And I want to spend a little more time on this because I think you're going to see a lot of commonality between what they do and what we do. Okay. So the ASIC design process has to use an Autorouter. Just they don't call it an Autorouter, they call it a place and route, or a PNR. And that's kind of important to know because if you're ever interested in researching this, if you type in Autorouter, you're going to get a lot of different hits. But if you're interested in seeing the algorithms that they use specifically in the ASIC community, you better type in place and route because that's what's going to give you more fruitful results in the search engines. You're dealing with millions of connections, and you are dealing with millions of transistors. It would take years to do this by hand. Okay? And unfortunately, and we all know this market over here, this market moves in weeks. And what was really popular today, next year, no one's going to even remember that it was even there. They've already moved on. It's a very, very competitive industry. So they've got to use these Autorouters in order to get these things out in these very, very tight market windows. So what is the process? Okay, and so what you're going to see is this process is very similar to what we would use, and I'll go through our process here just after I kind of review this one here. First and foremost, in the ASIC process, they have to write a script for each of the projects. This is why they still use Unix, and they use a command in Unix called the makefile. And what's interesting about some of these commands like the makefile or the make command in Unix is that they write entire books alone on this one command. And unlike us where we have to go into a program, most of the time most of us will go into a program and we do things. It's very rare that most of us will use some type of API outside of it. But in Unix, a lot of times you make a script or a makefile and you command it from the outside. So you have an engine and you tell it what to do, what options you want turned on, what things you don't want turned on, what rules you can set, and so on and so forth. And then once it's done, you can command it to kick off another run or to kick off another program and so on and so forth. So they make heavy use of these things. What's interesting about those makefiles is that, again, they are very custom for every single chip that they make. They may have, like I'll say, a template that they kind of run off of, but they, in the end, will totally customize it based off of the need of that chip. And there's also rules and strategies for each of the technologies that they use. And what's interesting about their industry, we don't really have to worry about this, but in their industry, depending on which company you're going to go to make those chips, they have to in turn give you back, they have to give you the libraries, they've got to give you the rules, and they've got to give you the strategies, and those are all placed into the custom scripts or these makefiles. They take hours to run these things. And so interestingly enough, those people who are in the ASIC world, and I think we still feel this here on the PCB side as well, but in the ASIC world, it's not a 9-to-5 job. They kick these things off. They got to constantly monitor them. If they fail for any reason, they got to investigate why that happened. They got to tweak their scripts, and they got to get it kicked off again. Each project will be run dozens of times through these Autorouters. Okay, the modifications are constantly happening in the design. So you also have to remember that they have like 20 individuals working on these particular designs at any given time. And what they also do is they start pushing things over to the route side before the design is complete. Now for us, that's really foreign, right? We want our design to be complete first, and then we start doing the route. But in their situation, they just want to see if they can even fit it onto the chip. And so they'll start these runs, and they, with the intention of just throwing them out later on if they have any type of modifications, or if there's a failure for that particular process or the run on that one to have completed. And lastly, and this is what's most interesting, these tools are $100,000 tools. And it's a very, very competitive industry. There's a lot of money in this. And what's interesting to me is that even if you run this thing dozens of times, and you've got your scripts all nice and set up, and you finally got it down to where it seems like it's going to work, you still will have to go in and close the timing violations there. So no router, even though it's $100,000, and even though it's state-of-the-art and it's the best one out there, does it perfectly. Okay, so if they can't even get this thing to run perfectly, we have a kind of a unrealistic expectation that we can get a PCB router to run perfectly as well. So what about our process? Well, in our process, we have rules and strategies too. So fortunately, we don't necessarily have to make a make file, though I suppose you could make some type of script to kick these things off. But there's rules which are our constraints, and our strategies are really kind of a way of tweaking the engine, because what you're going to see is that routers don't necessarily have a one-size-fits-all. A lot of these routers, especially even like the Situs router and Altium, actually has several routers built into it, and we're going to see this as we kind of go along here. And that's true probably for Mentor, for Cadence's Spectra, and also for the Zukin routers as well. Each project could be run dozens of times, and we'll talk about a little bit of strategies that you can do. In fact, a lot of the stuff that you're going to see later on are experiments that we were doing. So I've run these things many, many times, and I look at them and say, that's not too bad, but let's try this, or let's experiment with this. And so the expectation that's going to run right the first time is kind of unrealistic. More often than not, what I find is I want to run it completely as is to see what I get. And if it looks really bad, then I'll pull back and say, okay, why does it look bad? Are my traces, my spacing not right? Should there be critical signals that I need to do first? Are there other signals that really are very problematic? Is my placement correct? And so as a result of this, I should have an expectation of having to run this several times over until I get something that's very optimal. Okay. Cleanup is still very, very necessary. You're going to just see that. You're going to see some really weird and unusual routes, and that's just the byproduct of the router. So just be aware that once you've kicked it off, it's like, aha, I came back with 100%, no contentions, no violations, but you need to still look at it because you're going to see things that say, this is really, really goofy and I can't have this, and you're going to have to do some cleanup. Now, originally when I put this together, I was going to give you a full history, and I was going to talk about all the different routers that are out there, and that's why this presentation was almost 2 hours long. And I had to pull it back a little bit saying, okay, there are a ton of routers out there, there's a ton of concepts out there. What do I need to give you so that you have a good feel for how the PCB routers work? Well, what I decided to do is I was going to focus on two of them. One of them is called the maze or the Lee router, and the other one's called the spatial router or the topological type of routers. You can see the one picture I took over here. There's others like the channel routers, there's the river routers, there's hybrids of these things as well out there. So if you go out there and you start looking for different types of routers, depending on what area field, like artificial intelligence or the internet or VLSI, which is also ASICs or computer chips, they have these different routers that are kind of optimized for each one of those industries. So it's amazing what's out there. The other thing I'm going to mention here before I continue on is that routing or auto routing is actually relatively new. The concepts are not new. They've been around for a long time. It's just the computing power wasn't there to do it. And it really wasn't until the mid-1980s that we had the horsepower to do it, and it really wasn't until the mid-1990s we had the memory to do it. So keep that in mind, that you may say, like, why does this seem like it's such a new industry? Why is this area only just really starting to come into bloom now? It's just because we just didn't have the real horsepower necessary to do it. So let's talk about the maze router. So the maze router is an interesting thing because this is probably the most fundamental and the simplest router out there. It was designed by a fellow by the name of Chester Lee. That's why sometimes you may come across something on the internet that calls it a Lee router rather than a maze router. It was his concept back in 1961, and I'll give you kind of a little history here. In 1959, Professor Moore comes out with the concepts of how do we get something from point A to point B as quickly as possible along with obstacles. So he comes up with a concept paper. And by the way, Professor Moore, if any of you are electrical engineers out there, you may have heard of this individual before because he was also credited for the Moore state machine. So if you've ever done an electrical, let's say a digital 101 class or 102 class, you've probably dealt with state machines, and there are two types. There's the Mealy state machine and there's the Moore state machine. Well, Professor Moore is the one who came up with the concept of the state machine for the Moore state machine. Okay. In addition, what's interesting about Moore is that though he was an electrical engineer per se, he was very interested in artificial intelligence, and so that's why he was looking at these concepts of how do I route from point A to point B, or why am I coming up with state machines, because he was very interested in artificial intelligence. So this fellow by the name of Chester Lee comes out from Bell Labs. And what's interesting about Chester Lee, and the reason why we try to give him a lot of credit here, is because Moore's concepts were very abstract at the time, whereas I'll say Dr. Chester Lee, I'm not even sure if he's a PhD or not, but let's say he was the one who basically said, I'm looking at what Moore has done over here, and we can apply this to printed wiring boards. And if you take a look at what these boards looked like back in the early 1960s, there would have been a definite need for this because, again, what they were doing there is you only routed on one side. So the top, what they called, and we still to this day call it the component side, is where you place all your through-hole components, and on the bottom side is where you would solder it. And the idea behind these early printed wiring boards is that you didn't want to have to jump over anything because this is just prior to IBM coming out with the concept of through-hole vias. So the idea is like, how do we route this so that we don't have to necessarily jump over anything, or to avoid that as much as possible. So that's why he thought that the idea of this thing called the maze router was really useful. What's also interesting about this, again, the computing power at that point in time, the computers existed, but they were massive systems. Very few people would have had any type of access to them. So again, most of this was mathematical concepts or things that they would have to have done on paper. Okay. The maze router is considered to be the simplest. It is something called grid-based, and I will show you an example of what grid-based means here in just a moment. It's probably what you think it to be. And all wires, the idea is that all wires have 2 pins, okay, that you have a point A and point B. And even if there are multiple connections to a certain point, you're not worried about those other points. You're just worried about point A to point B, okay? And they call it a source and a target, by the way. The simplest of the maze routers are only done on one layer. So there are modified versions of what they call the maze router in which you work on multiple layers, but I'm going to show you how it works on one layer. And everything there is orthogonal. There are no 45-degree angles. So let's take a look at this. What's the initial strategy before we actually look at an example of it? The strategy of it is one net at a time. It's like, let's get this thing routed. And secondly, let's route this optimally. Let's find the shortest path possible. The problems with this is, number one, and this is what's very different between us and, let's say, those folks who are doing network routing or even those people who are doing artificial intelligence. When they get from point A to point B, they're happy campers. But in our industry and in the ASIC industry, what our solution is the obstacle to the next problem, right? We basically create our own mazes. So we have path blockages, and then there's no consideration whatsoever for future events. It's not smart enough to look around and say, oh, I see that this pin above me over here really needs to be routed first before I address this pin below me, right? It just doesn't think it out. It just says, okay, what's the next net? Where are they located? And let me see how I can get this net from point A to point B. And that's why a lot of times when you look at some of the routing results, you're like, this is crazy. Why did it do such weird jogs? It's because it didn't know the order, or it just took the order let's say when I say know the order, it didn't understand the proper order because it's just going down a net list and say, well, this is the next list line. I'll take this one. Here's the one after that. I'll use that one. And that's all it's going to do unless you somehow give it some priorities. The smaller the grid, the more memory and the more processing required. Again, up until really recently, now we have gobs of memory. We've got a tremendous amount of horsepower in our computers. We just didn't have this type of thing, so they had to be very careful about the grids that they were using. So what are we talking about the grid over here? Well, the idea is that let's say we have a source and we have a target. And what you're going to find with the maze routing process is very short-sighted. It really can't just look over here and say, oh, I can just simply go over here. Because first and foremost, it doesn't know anything about anything being diagonal. It either knows up or down or left and right. And the two options that you have over here is you either go horizontal or you go vertical. Or you have a bend. And again, the bend has to be 90 degrees in this very simple maze routing. Okay? And there's 3 parts to this. The first part is to expand this out, and you'll see what I mean by expand it in a moment. Once you get the solution, you backtrace to the shortest path possible, and then you clean it up. Okay? By the way, just as a side note, this was a really wonderful video that I had come across to explain this, and you can see it over here. It came from the University of Illinois at Urbana-Champaign, and I would highly recommend that you take a look at this. I've got the link down over here. It's about 16 minutes long, but I caught what I figured to be some of the most critical things for you to understand how this maze routing works. Because if you understand how this one works, you pretty much understand how all grid routers work. And that's really important because a lot of routers out there are initially started off on a grid. Okay? So what they're doing here is they're expanding something. They're expanding out. And what you do is you basically provide what they kind of call a travel cost to this. Now, in the simplest examples, it's really nothing but a sequential set of numbers. So S is where we start. We assign it 1. And from where we start, we assign the next number to the left, to the right, top, and down. And once we've assigned those numbers to it, then we go to each one of those numbers we've just assigned and we assign the next set of numbers to it. And as you go along over here, you actually get a wavefront, but it's diamond shaped. So if you follow along with my cursor over here, we go 4, and we go all the way down here. And if this actually expanded off the grid, then we would also see that this is kind of like a diamond. And it keeps on going until it hits the target. So that's what it's going to do over here. So you can see that this could take a lot of time and this could take a lot of memory, but it does get the most effective route orthogonally. Once you've got it, it's going to back trace through. So it's going to say, oh, I got it. So now it's got to count back and to figure out which is the shortest path it could have done. Now, obviously, the algorithm is going to have to either start vertical first or horizontal first. In this case, it started horizontal first, and it backed, and then it went vertical afterwards. And then lastly, you have to do a cleanup. So a part of this is having memory to know that these particular cells are now blocked off, or they call them nodes, depending on which algorithm you're using. And that's how the maze process works. Okay. Here's another example. The professor is showing this, didn't have time to type it up over here. He just drew them in. But you can see here's another example where they put another source and target. But by the time it got to the target over here, it finished with 9 steps. That's why you don't see it completed over here to 10, 11, and 12. There's no need for it because it's trying to find the shortest path possible. All right. I wanted to show this algorithm over here. This algorithm has been around for a very long period of time, just as old as the maze router practically. However, it's only been more recent that it's being used for 2 reasons. Number one, again, the horsepower of the computers, and number 2, a lot of people are showing interest in artificial intelligence, and the A-star algorithm actually does a really nice job with it. Okay, so it was actually developed in 1969, but because of the horsepower that we didn't have in the computers, it's like, we'll deal with the maze router, we'll deal with things that are a little more simpler than something of this nature. They certainly didn't have the memory for it back then as well. What it does allow for is 45-degree angles, and it also takes advantage of all the data being collected. So what's interesting about this is that, again, it looks very similar to the maze router, but they've enhanced it. So first and foremost, what you do is you actually provide a number to it, and they call this the travel cost. Now, in the other one, we just saw a sequence of numbers. But here, you can change these travel costs as you see fit because you can get different results depending on where you, how you set these up. Now, most of the A-star algorithms that I've seen out there, at least the videos that people have put out there, almost always assign either horizontally or vertically 10, or if it's diagonally, they put 14. But again, you can change these numbers later on. And of course, if you have a little more insight, there's certain things that you can probably add into these numbers or subtract off from these numbers to assist them, right? None of these algorithms are just run as is. People tweak them to optimize them. So where do these numbers come from? Well, pretty much through Pythagorean. The idea is that if your 2 legs are each 1, your hypotenuse is going to be radical 2. That's equivalent to about 1.4, actually a little more than 1.4. And so what they do is they say, okay, let's multiply everything by 10 over here, and that's why you get a diagonal default of 14 and the vertical and horizontals of it being 10. All right, we collect a lot of data over here, and so not only collecting information about the cell that we're in, we also have to collect information. I'm going to briefly go over this here. I think there's a lot more details to it, but the idea behind it is that unlike the other router where we just kept moving the wave forward until we got to the target, this particular algorithm wants to know not only where it's going, but where it came from. And more importantly, what you're going to find is that not only where it came from, it wants to know that, hey, look, you took all these steps to get to where you are. Was this the optimal path to get you here? And it will correct it. And that's what makes it a very, very powerful algorithm. So just to give you an example over here and to talk a little bit more about these travel costs, so there's actually 3 different travel costs. The first one is known as the G cost. And the G cost is saying, like, this is where you are and this is where you've been. Where the green is the source and the blue is where you currently are. These black dots over here are the obstacles, and the red one is your target. So far in this example, our G cost is actually 20 because we had to go 2 nodes. So 1, 2. So that's our G cost. The second cost is the H cost, and the H cost is where I am to where I'm going to go. And what's interesting about both the H cost and the initial G cost is that obstacles don't, the obstacles are ignored, at least initially. And then later on, when they do further calculations and compare, then they have to take the obstacle into consideration. So in this example over here, the H cost was 48. because if we actually went orthogonal the entire way over here, I believe this comes out to 60. So this is 10, 20, 30, 40, 50, 60. So it was worth our while to use the extra travel costs of the hypotenuse, or the diagonal, to reduce that from 60 to 48. And then lastly, we take the F cost, which is really nothing more than taking the G cost and the H cost. And what's important about the F cost is that's the one we look at initially to see which direction we ought to be going. So again, very similar to the maze, what do we see over here? We evaluate our start point and we look at left, right, top and down, and all of our diagonals. And the number with the lowest F cost is where we're going to go with that. And that's exactly what happens over here at 70. And by the way, the three numbers you see over here, at least the way this individual, and by the way, his name is Justin Deitel, he did a phenomenal job with this particular little video. And there's a number of A-star algorithm videos out there. I just felt he did a really great job with it. He did this in MathCAD, and so what he was doing was just demonstrating where the H cost, the G cost, and the F cost were coming from. So in the top left corner, you see the G cost. The top right corner, you see the H cost. And in the bottom, you see the F cost. And what he's showing over here is the logical progression as it's going along here. And if the H cost is, if the F cost is the total cost, is equal in another area, then it has to look at the H cost. And the H cost will be the differentiator at that point. And what I also mentioned earlier on is what's neat is that as this is progressing along, it evaluates back to where it started. And if it finds that there was a shorter path to go, it's going to redraw that path. Now, what's interesting down over here is you'll notice that the shortest path would have probably been this vertical, horizontal line here. But the point, one of the reasons, and I mentioned this earlier on, that it doesn't see this is because it hasn't evaluated this one yet. Okay. And as it goes along, it will evaluate it. And once it evaluates it, it will correct itself. So here's the finished result of this. And the idea behind this is that as it went to each one of these points, it may have ping-ponged back and forth here as it was looking between the F number and the H number and possibly even the G number. But at one point, it realized that going this path is going to be shorter. And so it ultimately finds it. So it's a really cool algorithm. And I think a lot of routers actually use this, even though they don't call it the A-star algorithm, because it looks back and says, can I do a better job from where I started off? And what's also neat about this is because you can change the costs, and this is what he did over here, is that if you change the G cost to make it more expensive, what happens over here, well, look at all the evaluation. Each one of these little, they're all pink dots, but these basically mean that all these areas got evaluated. And it would take a lot longer to do that and a tremendous amount of memory to do that because of all the information it had to store up. But it gives you the optimal route. This would be the optimal route to get around this obstacle and get to your target. Okay. Excuse me. The H cost, if it's more expensive, you can get to it very quickly. So notice how few pink lines we've got, or pink nodes we've got over here, but also look at how jagged this line is over here. Okay. So there's a balance between the two, and that's what these routers can be set up to do. So keep these two in mind, the A-star algorithm and the maze router. Those are the ones you're going to see, because if anybody tells you it's grid-based, it's going to probably be either the A-star algorithm or the maze router or a flavor of it. So again, they had to use a grid in order to do this. This grid could be arbitrary. I know that in the Altium Situs router, I'm not even sure what they set the grid to or how it determines what its grid size is going to be. Okay. Now, just a little bit talk about the Altium Situs routing, because again, I think that what they do in the Altium one is not too far different from all the other ones as well. Because yes, they do use a grid-based router initially, but then they go to a shape-based router or a topological router afterwards. Okay? And so what is the concept of a shape-based router? Well, it doesn't necessarily use a grid. It actually uses rectangles. And there's a whole paper written about this here. Well, this is a more recent book. It was very, very mathematical, to say the least. If you're good at reading those type of things, you've got to read it very carefully, because each sentence is probably a thesis all its own. But nevertheless, you have to use these bounding rectangles, and you use something called rectilinear expansion in order to calculate a couple of things there. So probably the best way for me to do this, and this comes straight off of Altium's website. They did a really great job explaining how the Autorouter works, and it's 4 steps. So first and foremost, they're pretty much starting off with a grid or a maze router. So they're starting off at this pad over here, the surface mount pad, and they're coming to probably what looks like a through-hole pad. And so they want to make sure it just routes. But then what they do with this interesting is that now they start pushing in the shape-based router. And originally I thought the shape-based router meant like you had a trace and it was kind of hugging or pushing along the trace. That's kind of true, but really what it's using is bounding rectangles. And you can see that example right over here. So here's what it does is it's going to put a bounding rectangle anywhere along the path that this initial route took. So you can see this bounding rectangle, and you can assume that the black lines that are acting as the boundary here are also the boundary for this bounding rectangle. And once you've got that, then you move over to the next one and you put that bounding rectangle in, and so on and so forth. And then it can use this rectilinear expressions to kind of come up with something. What's really interesting about this is that after it's done here, they kind of create a number of different, I'll just call them hypotenuses in a sense, right? So they calculate these things, and if you really look at what this wire is doing, it's following or hitting along each one of these wires until it gets to where it is. I should make one other note here too. You'll notice that there's actually boxes over here. So even though the path went up and around over here, it looks like the tool is making an attempt to see if it could actually use one of these smaller boxes to cut through rather than go up and around. And that's what you see here. And then finally you get what's called a glossing. And a glossing is really, and there's a lot of science behind it because there's strong glosses and weak glosses, but the idea behind it is to try to make this route look as clean as possible. And that's what they mean by glossing it. Okay, so with that being said, what I want to do is give you a couple of recommendations as to how you can work the Autorouter to your advantage. So I think first and foremost, and I don't necessarily have a slide for this, and I make brief reference to it, what I have found through all of the trials and errors that we've made trying to get this presentation together is that if you're just going to try to kick off the Autorouter, try to do a complete board, you're probably going to be a bit disappointed with it. And more often than not, what you want to do with the Autorouter is use it where it will best serve you, but that's after you've already done things that are critical to make it successful. And these are the things that we're going to talk about. So first and foremost, placement is absolutely critical. If your placement is all over the place, it's going to have problems. So just to demonstrate this here, what I did was I took this board. It's a board I made about a decade ago when I first learned Altium Designer, and it was an 8053 board. And I really like this one because we've been able to, it started off as through hole, and we've added in a couple of surface mount components to shrink it down a little bit, and that's kind of helped us try some various experiments for this particular webinar. But what I did over here is I said, okay, I'm just going to route this board based on the size that it is. It took 2 minutes, 38 seconds, no contentions. Then I took the same board, I unrouted it, and then I took K8 and K2. These were the two connectors that we had over here, and I swapped them. And they are definitely not in their optimal places. And I ran it again. And you can see it pretty much double the time necessary in order for it to complete. As a matter of fact, when I look up here, and this is that white box that I put up here on the top, that if I did not give this little extra area up here, I think it would have really, really struggled to get it all the way up and over into the 8053, which is represented by this large footprint here, and vice versa. Okay, so placement is definitely critical. If you're not careful with the placement, there's a rule we're going to come up to. If you can't route it, it can't route it, and most of the time it has to do with placement. What do you need to do? Well, you got to be able to escape it. So again, if I jump back to this example over here, you can see that I don't have a lot of escape room here. I don't have anything to the top. I don't have anything to the left. I'm not doing anything to the right. That means I got to escape everything out going this way. So I'm really cutting my escape routes here, and that's why you want to be very careful of putting things into the corners, especially things like BGAs. Okay. You want to choose surface mount over through hole. That's what we found here. So the original designs did have a lot of through hole here, and over time we were able to, well, actually through these experiments, we reduced them down to their surface mount equivalents where we could. So we didn't want to fake anything here. Anything that we could find and replace, we did put a surface mount on it. This is a EEPROM, which we couldn't find a replacement for, so that's why we left it in there. Okay, but we still got it down to a remarkably small space, even with all the things that we reduced it to. And by the way, as a side note, the original board I had drawn out to be 3 by 5, so we were able to reduce it quite a bit for these experiments. What's interesting about surface mounts is that we have the option to use vias. And that's a nice thing because vias actually do cause a lot of hassle, not only in terms of the real estate on the layer you're on, but also on the other layers that you're working on as well. Secondly, if you do have to use a via, more than likely the via is not going to be that large, right? In comparison to a through hole, where this particular EEPROM, each one of these through holes is 60 mils in diameter. So that's taking up a lot of board real estate over here. So that's the other thing to keep in mind too. So if you can keep the surface mount, all the better. If you can't avoid it, that's not a big issue, but that's the recommendation here. And then lastly, have a voice in placement, because something like this that I'm showing you here could actually happen because it's not in your control, right? And what we're finding more and more when we talk to our customers is that really in the past, maybe the electrical folks kind of owned the design or had, well, say, the dominant hand in the design, but there's companies now that the mechanical folks have the dominant hand in the design. What that means is that they're the ones who are doing the initial designs, and they're they're putting together the initial concepts, and the board is taking a secondary role. And what we found with a lot of mechanical folks, it's not necessarily a bad thing, but it's just they haven't been taught these things. They don't necessarily understand routing. So again, you can pack a lot of stuff into these boards, and they can see that and say, well, you can get all these components onto the board, but they don't necessarily understand the difficulty of the routing of it. So that's why you want to have a voice in that particular area. The other group that seems to be getting more dominant in there is marketing, because marketing wants to put out things that are flashy and cool, and a lot of times they won't go directly to the electrical folks. They go to the mechanical folks to see if they can put together a really cool box or something that will make the product look really great. So they go to the mechanical folks put the box in, and then the electrical folks are asked to put, to almost kind of work miracles within that box. So that's why I say have a voice in the placement, because otherwise it's going to be something of this nature, and it's going to be very difficult. When I say something of this nature, I'm talking about the difficulty of routing this, or at least even using an Autorouter for it. Okay, power and ground. You know, in the past, we used to draw out the power and the ground, and to be perfectly honest with you, if you want the Autorouter to work with any efficiency, you really don't want to be wasting trace or signal space for the power and the ground. And there's a number of different reasons for that, but you remember, everything that we draw out becomes an obstacle for something else. And more so, the power requirements of today really require something that's a little more solid than just branching out a bunch of VCCs and grounds. Okay? For example, one of the things that, you know, you may say, well, I'm not doing high-speed design, but definitely in high-speed design, you want to make sure you have ample power or ample copper where your power is going to be, so that if a signal is being sent out, that the pushing of that signal out, because it draws a lot of current, doesn't drop your rail down or your voltage down. And you may say, well, I'm not doing high-speed design, or I'm not using an FPGA. But what you find today is that even like a 7400 part, which was used, let's say 30, 40 years ago, they still make these parts. They put them in smaller packages, and they put them in smaller die. And they do try to keep to the characteristics that they had 30 or 40 years ago. But the trick is that the rising edge of these are much sharper than they were 30 or 40 years ago. And you have to remember, in high-speed design, it's all about the rising edge. And if the rising edge is being pulled up very sharply, okay, you're pulling a lot of current, and in turn, you're going to drop your rail, and you want to avoid something called rail collapse. So this is just to give you an example over here of when I took the board and I routed it on 2 layers, and I said, okay, route the VCC and route the ground. And you can see all of this distributed you know, the distributed wires going on over here, okay? And I also did a run of this as well. So again, same size board. One of them was 4 layers, took 2 minutes, 38 seconds. The other one did complete the route, but again, it took twice the amount of time. So my recommendation here is that if you can get away with, obviously, polygon pores, they are a big help, or if you can also put planes in there so you can drop them down to the planes, that helps out tremendously as well, so that you can free up your routing space. In terms of real estate, you know, real estate also will play a role in it as well. And you can see what happened over here. So this is pretty much the exact same board, or at least the same type of components here, where we started with a 3x5 board. It took a little bit over a minute to complete. Here's the situation where we left everything the same, the trace and the space requirements, just that we really shrunk everything down to, you know, to 34%. And it took over 3 hours, 17 minutes, and it didn't even finish the route at that point in time. Now, just as a side note, I didn't have time to add this in, but we did some other experiments, and we found that, hey, you know what, the trace in the space over here actually is another major factor in this, because that doesn't seem that big, right? It's 10 mil trace, it's 13 mil space, but we actually moved it down to 7.7, and this actually did route at that point in time, and it only took a couple of minutes. So it's amazing to me that even a little bit of trace and space give on this had a dramatic impact on it. So keep an eye on the real estate, but also keep an eye on your trace and your space as well. Obviously, you don't want to push your trace and space down to a point where you can't manufacture it. But what happened with this was that I asked a colleague if they could route this out by hand. He asked me if he could reduce the trace and space. I said, certainly, but I have to run it again. And when I ran it again, I actually got very different results. And in retrospect, when you think about this, you're dealing with a lot of different things. When we think about the router, we were just thinking about, hey, are we going to hit the obstacle or not? But we also have to remember the router has to take into consideration the clearance area as well, right? And there may be clearances on both sides, and that takes even more computation to do it. Vias, what we found about the vias are kind of interesting over here. So what happened initially, and this is give a little story here as to why we think it's the vias, is that I had taken our board and I shrunk it down to these dimensions here. And it took me 5 minutes, 13 seconds to run it. Now, I told my colleague initially to do the same thing. Before he had shrunk it down to this small, he had shrunken it down to this size. And he ran it, and it only took 1 minute, 48 seconds. I'm like, that's kind of crazy. His board looks a little bit smaller than mine. What happened? So when I started doing the analysis of it, I really found that his board area and my board area weren't too far off. And neither was the component area, the routing areas. But he had far less through-hole vias. Okay, and that causes a lot of obstacles in the end, and so there was that factor to play in there too. One of the things that I think we'll probably be doing here at 9.Connects over time is that we do believe that there's some type of ratio that we need to look into as to what does it take between the board real estate and the component real estate. And in the past, apparently there was an equation for this. In talking to some of my older colleagues, they said there was an equation, but that everything was through-hole. So we have to take into consider other factors now for surface mount, and that's something I would have to do a little more research on. But we did find that the less vias that we had, the faster and easier it was for it to route. Routing priorities, you know, the thing is that you're going to have to know these better than anybody else, okay? Routing priorities are just your clocks, your DDR memory types, your reset, your power. Don't let the routers try to do this stuff. You're probably going to be best at it by far. Make sure, for example, the escapes, the short signals or the escape issues that you're dealing with, sometimes you can draw those in a lot faster because they're just very convenient to draw in. There are tools, I know Altium, for example, has a breakout tool. It works out rather nicely, so you can break it out using that particular tool. Okay, differential pairs, you've got to route those because they've got to be matched, because if they're not matched, they're not going to work. So that's why I put down, this is one of those areas where you're going to know better than any router as to what is necessary to do here. And these little pictures here, these examples that I'm bringing up, you can see here that, for example, this 81 to this 81 over here, this is something you'd want to address right up front. Because if this was left until later on, where would you escape it to? How easy or difficult would it be for you to get from A1 here to this 81 over here? So that's why we recommend dealing with those short signals first. Also down here, just another example, you've got two components basically sitting on the side of the board over here. So where are they going to escape out? Well, they can probably do a little bit of escape to the left and the right, and they're obviously going to have to escape out to the top. But now they're practically on top of each other, so both of them are trying to get everything out going through the top. So it makes it very, very congested. And that's why it's, again, if placement is certainly an issue, but the priority that you give to each one of these signals is also going to be an issue too. Routing strategies. So you notice I haven't really talked about routing strategies about this, and that's just because I didn't really want to talk about one particular router. The key point I want to make to you is that one router, the router that you got is not one size fits all. And any of these routers are probably going to provide you different tactics or strategies that you can use in order to get the job done. And one thing to keep in mind about all these different strategies over here is you don't have to run every single one of them in one pass. You may run one of them and say, okay, I found these all off the plane, this particular signal, usually it's ground. All right, I see what it did. Now I can route the rest of it by hand. Or, okay, now that I've got this, let me save this off and let me try to do what they call a memory. Basically a memory pattern, because I've got a lot of things going out from this one chip in parallel to other chips. Okay, so those are the things that you can take a look at and try. Of course, the rules are very, very important. They are the constraints. These I tend to believe would be the rules that you would see in any of these routers here, your clearance rules, your trace width, your via dimensions, your routing layers, whether you'd want them enabled or not. Okay. Altium also happens to have corners, topologies, fan out, and routing priorities. But you want to definitely take a look at the rules that are going to make these things happen. But more importantly, if you're getting some really weird route, you may want to see if one of the rules needs to be tightened up a little bit, or even loosened, depending on if you're even able to complete the route or not. You got to review the results. You're going to get weird things. And you can see all these little weird things that we've seen as we've been going through it. You're going to have to clean these up. And so you can see some examples over here of things that probably should not have happened, but they did. And, you know, that's just kind of unfortunately a byproduct of these routers. So look for loops, look for odd branches. And by the way, I think to me this is takes just as long as someone hand routing these things out. And I think this is what happens with a lot of us, is that we say, yeah, the router does some really weird things, and now I got to evaluate every single net and make sure it looks clean, and that takes a long time. So that's kind of where the trade-off is that, yeah, it routes it really quick, but now I got to spend just as much time cleaning it up. Well, is it the same amount of time for me to just route it by myself? So those are things to keep in mind as well. Another recommendation, this comes also from a senior fellow here at 9.Connects, was he recommended don't rip up everything in mass. Like initially, you may want to do it just to try a couple of routes and say, yeah, that worked or that didn't work. And if it didn't work, let's just see if these rules change it and rip it up again. But once you start really get going with it, you may want to just not only just review what you got, but see if you can remedy what it is. Because sometimes you may just spin your wheels just saying like, well, I want this to be perfect, and you're constantly tweaking it and it'll never be perfect. Whereas you say, you know what, it's good enough, I can clean up the rest of it. Okay? And that's where, where you have to make a judgment call on that. And then another thing is that a lot of these routers have what they call a cleanup. And this is one of those things where two rights make a wrong, meaning if you run a cleanup and you try to run a cleanup again, the second cleanup will not necessarily clean up the first cleanup any better. And remember, and I showed it earlier in the slides there as we were going along, as these wires are being, the proposed paths are being done, well, what are they doing? Almost all of those are diagonal, right? And then it finds finding that last path. So if you have a lot of diagonal lines, you're trying to optimize diagonal lines with diagonal lines, and it really doesn't work very well. And if anything, it's going to make it look really unusual. And more importantly, these cleanup things aren't necessarily smart enough to look ahead. So they're not looking and saying like, well, okay, I'm dealing with this point A, point B, but point C to point D over here probably should be better suited if I dealt with that first and then go into point A and point B. It's not smart enough to do that. So just keep in mind that cleanup of cleanups, you can run it once, but running it twice is not going to buy you anything. So other thoughts they've got on this, you know, again, if you can't route it yourself, the Autorouter will not be able to route it. You're the best router out there by far, okay? Start with the shortest lengths first. I've mentioned that before. I really want to emphasize that point. Just start with the shortest ones first. Draw them yourself if you want to, because they're the toughest to escape, and you have very few options for that. And then always save a copy of your work prior to, you know, you doing another route or an auto route on it, so that you can, you know, if you say this is terrible, I don't like it, then you don't lose any of that work. Take advantage of the interactive routers being provided. So I always give this history about Altium and, you know, the Situs router, especially when I used to do support for them. And what was interesting about it is that I think they did go down that auto routing approach for quite a while, and then they realized that there are certain things that auto router could never do right. It was always going to be done better by the user. And what a lot of users were really kind of saying to them is that they wanted the ability to do things that didn't make it so difficult. And that's why you see these things now called interactive routers, right? Where you're the one driving it, but they made it a lot easier for you to drive it. And that's where we're seeing a lot of all the EDA tools are going, saying, hey, look, I'm going to get you from point A to point B, and you don't have to click every single way to get there. We'll propose some routes for you, but in the end, you're the one who's going to accept it or not accept it. You're the one who's going to say, start at this point A here, let's get you to point B. And that gives that ability to the individual. And they've done, I think, a really phenomenal job with that in the last decade. So definitely take advantage of those interactive routers that are being provided there. You know, the things like the fan-out tools or the interactive tools. And look, you know, one of the other nice things that Altium does, I know other tools do it as well, is that if you actually have some particular router that you think is better, they allow for what they call a do file to interact with it. So you can pass the do file back and forth between, for example, Altium and an external router as well. So they're not just saying you've got to use only the Situs router, there's other options as well. And the last thing I just want to leave you with here is, and this is what I'm finding, is that experiment with it. If you're interested in what these things, try them on simple boards. You really don't have to create anything super complex to prove that it works or prove that it doesn't work. It really only needs to be, in most cases, it really just needs to be two connectors that you put up there with a lot of keep out blocks all over the place, and you can really try some neat stuff with that over there. Okay. So that's our presentation here on the Autorouter. And I don't really have, if you have some questions, feel free to put them up over there. I'm just going to give a little brief overview of us here at 9.Connects. Obviously, topics of this nature are very important to you. You know, just don't feel that you're out there on your own, right? A really great example of that is this Autorouter stuff. Because when I was out there looking for this stuff over there, what I found was either people just explaining how to use an Autorouter in a particular tool, or they were just dismissing the PCB routers as being inferior to manually routing. And when you really start digging more and more into it, the Autorouter can actually be yet another tool in your toolbox to make it more useful. But it required us to do a little bit of research to come to that conclusion. And that's why we're here. We're looking into these kind of things because we want to be a PCB-centric organization dedicated to training, coaching, consulting, design, and layout. Any aspect of it, we want to assist you with if you need some help with it. What are the topics we know? High speed, RF, power, design for manufacturing, libraries, mechanical. We have well over 40 different webinars that we've done the last couple of years over here, and any of these topics we've talked about. But if you need us to go into more detail, feel free to contact us about those questions. Because in the end, we want to get you beyond your technical hurdles. We want to confront those technical hurdles with you. That's what the Autorouter was to us, is a technical hurdle. Is it really something to use, right? And hopefully you're kind of getting a feel that, yeah, it's there, but it's not that big of a hurdle, and it might even be of a benefit. But ultimately want you to get the work done as well. Obviously, if you want to see a little more information about us, feel free to check us out here at 9.connects.com. And we're always adding more and more to them.